Select the major product that forms from the following series of reactions. So if we look at what we're starting with, we have a relatively unfunctionalized molecule except for that benzene ring. So we have the benzene ring and we also have a methyl group sitting here, CH3. So we've got some sp2 hybridized carbons and then the sp3 hybridized carbon of that methyl group. So if we look at the first step, we're reacting this with NBS and light. So we need to remember what NBS is. And so this is the acronym that stands for N-bromosuccinimide. And so what we want to recognize is that this is a molecule that has a nitrogen-bromine bond that's fairly weak. And light is a way to cleave that bond homolytically to give us a small amount of bromine radical. So what these conditions are the conditions for either allylic or benzylic halogenation. And so this is a radical reaction. And one of the things this reagent NBS is a clue to us because we see this for allylic and benzylic halogenation. Light is also one way that you can initiate a radical reaction. You could also see heat, or this could also be initiated by peroxide, or some combination of these three are common conditions for initiating a radical reaction. So what the N-bromosuccinimide does is it provides a low concentration of the bromine radical. And so that's necessary when you're dealing with a benzene ring or an allylic system that has an alkene, because either of those pi systems could react with molecular bromine. So what this is going to do, benzylic halogenation, means you're going to replace one of the hydrogens at the benzylic position. So that's the carbon that is attached to the benzene ring. So after this first step with NBS and light, we will have replaced one of these benzylic hydrogens with a bromine. So we'll end up with benzyl bromide. Here is our intermediate. And so we have a primary benzylic halide now. And so this could undergo either SN1 or SN2 substitution. We can't do an elimination reaction with this alkyl halide because we need an extra carbon atom away from the benzene ring to make the alkene, and it simply doesn't exist. So this can undergo either SN1 or SN2. And what's going to determine the pathway with a benzylic halide, because although this is primary, you can get a resonance stabilized cation. So that does mean that SN1 is possible. It depends on the strength of the nucleophile. And this will determine the pathway. So if you have a weak nucleophile, so something like a neutral water or an alcohol, you would see this undergo an SN1 pathway. If it was a stronger nucleophile, like this cyanide ion, it is going to undergo an SN2. And of course, there's a lot more examples of strong nucleophiles that you've been introduced to before. So we expect that this is going to go through this SN2 pathway because of that strong nucleophile. So we have our cyanide ion. And so the carbon is where you have the negative charge. So this is the nucleophilic atom that is going to attack the carbon that where you have the bond of bromine, and then the bromine will be kicked off as a leaving group. And so we will have the benzene ring still. Make sure you don't forget that CH2 carbon. Don't just start drawing your triple bond. You've got to make sure you still have that CH2 present, and then you can have the triple bond to the nitrogen. And then we can take a look, and it appears that this answer matches A.